My name is Krati, and today I'm going to talk a little bit about transformers, their transformer architecture, and how it's being used in LLMs. The contents that we are going to cover today is going to be encoders, decoders, the entirety of self-attention and how it's so different from RNNs. And we're also going to talk about GPT and DeepSeek. If you don't have time to do it today, then those will be the upcoming videos in this series. Alright, before I start, I'd like to tell you that all of the sources that I've used in this video will be linked down in the description. I have definitely borrowed a lot from The Illustrated Transformer by J. Alomar. That's an incredible blog. I think everybody should go and check it out. Right, and so unless you've been living under a rock, you know all about generative AI and LLMs. And I think it's very important to also understand about the transformer, irrespective of whether or not you're a student of AI, because even though the research and the transformer is basically groundbreaking, even then I would say it's simple. Especially if you've studied it like once or twice, you'll understand that it's simple. Okay, and yeah, the paper is called Attention is All You Need by Vaswani et al. And it's important because generative AI is everywhere, and this is like the cornerstone, the building block of most LLMs today. Right, so the LLMs, or the large language models, are either encoder only, decoder only, or encoder decoder. This depends on the kind of output you want and the way that they have been trained. In the table in front of you, you would see that the encoder-only models are like BERT, Roberta, and DistleBERT, and their use cases are text understanding, classification, and named entity recognition. For decoder-only models, you've got your GPTs, your DeepSeek, Llama, and Falcon, and they generate text. They are used for making chatbots and code generation, anything that has to do with generative AI. And then there's encoder-decoder. They're used for translation, summarization, and question answering, basically something where you would need a series. Okay, now let's get started. So what is so different about this paper, and what is so amazing about attention that it has changed everything? Before attention, we were relying on RNNs and LSTMs, and they were pretty amazing in themselves, but they had certain drawbacks. Before we talk about the drawbacks of RNNs and LSTMs, here's a little picture for you to do a little recap, and if you're new to them, maybe you don't have to study the entire thing, just look here. So this is a feed-forward neural network. It's a simple network where you have different inputs, and they all feed information to the hidden layer of the neural network, and then it goes forward, and it's simple, and it works basically for anything that's not serialized. But for recurrent neural networks, they work a little bit different from the regular feed-forward neural network. Here, the information only flows in one direction from input to output, but in RNNs, the information is fed back into the system in each step via a hidden step, as you can see what this arrow signifies. RNNs allow the network to remember past information by feeding the output from one step into the next step. This basically helps the network understand context of what has happened before. It's like a little memory for it to have context. But as you can see, this works one after another. It doesn't have any parallelization, and that is one of the main drawbacks of RNNs. And because it only captures information in series, you will never understand long-range dependencies as either. And this is where self-attention comes into play for all of these reasons: parallelization, long-range dependencies, and scalability. But attention has now replaced all of this, and let's just get started with the architecture and attention. So yeah, the first step in the transformer architecture is the encoders. Number of encoders is equal to the number of decoders. In the papers it is 6. In the paper, the Attention is All You Need paper, it is 6, but it doesn't have to be. And output from one encoder goes to the next, and they are all same in the structure. So in the first encoder, the natural language is first broken down into tokens, and these tokens are then embedded into vectors, and that only happens for the first time here. And after that, the output from this encoder goes into the next, and so on. So that makes you think, if the structure of all the encoders is the same, do they also share the same weights and biases? Let's think about it for a second. So what is encoder doing? Encoder, except for the first step, it is not really changing the input. What it is doing is that it is because of the attention mechanism lying underneath, it is understanding different parts, different relationship between different parts of the sentence. So if the weights and biases were to be same in each encoder, then they would just perform the same task 6 times, and it wouldn't make any sense. So now, if the weights and biases were shared, they would limit the model's capacity to understand hierarchical features. And so what this basically means that when you start with the first encoder, it captures the lower level relationships between different tokens, and the higher level captures more abstract features like sentence level meaning. So if the weights and biases were same, the stacking would be redundant. So no, they are not same. Okay, moving forward. All right, so as we talked about before, that all the tokens are divided, the sentence is divided into smaller tokens, they are made into embeddings, and then fed into the encoder. The interesting thing is that all of these embeddings, they go into the self-attention layer at once. They don't go one after another. They are being processed in the self-attention layer all at once, and this is where the parallelization starts, and this is where it gets interesting. So we'll get into self-attention in just a minute, but after self-attention, each token's representation is updated. Each token's vector then flows through the same feed-forward neural network, but independently. So in feed-forward neural network, parallelization doesn't happen. It only happens in the attention layer. And from attention layer, it goes to the feed-forward neural network, which typically consists of 2 linear layers with a ReLU activation function. And that very broadly is the encoder. Let's zoom in a little bit more and talk about the attention mechanism. Okay, so don't give up in the middle of this. Stick with me. We'll get through this. So for the first step, we already know that the token is broken down into embedding vector. And it's just, you can use any embedding algorithm like word2vec to turn this into a vector. And the vector's dimensionality is 512. And with this, we also add positional encoding. What is positional encoding, you ask? It is because in attention layer, all of the tokens are processed simultaneously, you would need, in the end, something to tell you which was the first part of the sentence, which is the second word, which is the end of sentence token. You need all of that information, so positional encoding is also added. All right, now we have a 512 dimensional embedding vector. What do we do with that? We create 3 different vectors from it, each with a dimensionality of 64. And we do it by multiplying it with the weight matrices for query, key, and value. Okay, fine. We have 3 different weight matrices. We multiply our embedding vector with it. And now we have 3 different vectors, query, key, and value, each with dimensionality 64 and not 512. Okay, so far so good. Now, we compute the dot product between query and key transpose. We compute the dot product to understand the similarity, and we do it with between every query and key value pair, so that we understand. This is where understanding and important in between different tokens comes into play. This computes the similarity between how important each key is to a query. You can think of a key to be answering the query vector, and the dot product is going to reflect that similarity. Okay, after you've computed that, you divide it by 8 Why 8? Because it's the square root of 64, which is the dimensionality. And we'll get into more detail, just hang on. After that, you compute the softmax for normalization. So for those of us who don't know, softmax is basically a function that squeezes a range of values between 0 and 1. And the values that are most relevant will have the highest value. And it turns it into probability so that it all sums up to 1, and we have like a nice clean looking picture of probability of the next generated token. Then you multiply each value vector by the softmax value. And why do we do that? We'll just see that in a minute. Then you compute all the scores from the above step. You do this 7 more times. All of this process, you have to do this like 7 more times, because in the paper they talk about not just 1 but 7 attention heads. And because you have to, like, for the first attention head you'll have 1 pair of these matrices. In the second attention head you'll have different weight matrices for query, key, and value. So right, this is how you end up with 8 sets for each encoder and decoder, and this is called the Z matrix. After that, you concatenate the matrices and multiply it by the WO vector to give you a single value. So this is all of that gives you attention, that gives you the understanding between context, and this is how the transformer understands context. So this is a neat picture from Jay Alomar's blog, which makes it look simple. So, right, our input sentence, you embed it into a 512 dimensionality vector. You multiply this with weight of query, key, and value. You get your 64 dimensionality matrices. And yeah, you multiply it by V0, softmax, divided by 8, whatever. And then you get all of these Z matrices, you multiply it by W0, you get your final output. So this is multi-headed attention on one screen. Okay. Alright, but where did we get the weight matrices from? Why is the dimensionality 512 and what is 64? Why does it matter? What are multiple attention heads? Why do they have different matrices? How do we calculate the dot product? Why divide by 8? Why softmax? Why can't get blah blah blah? So many questions. Okay, let's start with the first one. Where did we get the weight matrices from? They're randomly initialized. So weight matrices are randomly initialized and they're updated during backpropagation. Next, why is the dimensionality 512? It doesn't matter. That's how they decided. These are the hyperparameters that the authors of the paper decided would work best, and that's how they are. Feel free to experiment with others. Okay, now what about multiple attention heads? Why do you need so many attention heads? Okay, so we need multiple attention heads because each multi-headed attention is going to talk about a different learnable parameter. So let's say if one attention head is talking about syntactical structure, the other will focus on semantic meanings. And if you didn't have different weight matrices for different attention heads, then they would just calculate the same thing. So that's why they're different. Okay, why do you calculate the dot product? I think we already know that. It's because it talks about the dot product between query and key value determines how much attention a token should pay to another token. If two vectors are similar, their dot product is high, meaning they should attend to each other more. Also, it's fast. It doesn't cost too much in compute, so that's an added bonus. Alright, and we also know already kind of why we need softmax, because the total weight could be positive or negative, and for the attention mechanism to become more interpretable and for probability reasons, we apply softmax. Okay, and why do we divide by 8? Like, it's important to notice that 8 is the square root of 64, which is the dimensionality of the vectors that we've calculated. It's because it leads to more stable gradients. They did some research and they figured out that the gradients were crazy well calculation, and if you divide it by the under root of the dimensionality of the key value and query vectors, you will have more stable gradients. That's it. Okay, why do we concatenate the output from 8 different attention heads? It's because the feed-forward neural network expects one output from the attention layer. You cannot provide it 8 different outputs. There has to be some mechanism to make sure that the feed-forward neural network receives the input that it needs. So you concatenate it and multiply it to have the dimensionality right. Alright, now the most important question. Why are we multiplying it with the value vector after softmax, or why are we multiplying it with value vector at all? Okay, so the value vector basically contains rich information. By that we mean it tells you about the word itself, whereas the dot product between query and key tells you which tokens to focus on, but it doesn't include the actual content. We're going to dive into a little more detail about this one. Okay, so we know that softmax converts scores into attention weights. It basically answers the question, how much should we focus on this word? And by multiplying it by value, it extracts the information, like what actual content should we use. Let's take an example. Say we have a sentence, she kicked the ball, and we're trying to focus on the word kicked, and by we I mean like your model is trying to focus on the word kicked, and it's trying to understand which words in the sentence are important with respect to kick. Alright, so for each word you have your query into key score, and this is like a lot of numbers, right? But if you have it scaled between 0 and 1, which is softmax output, it's easier to compare them. Okay, so of course kicked with itself is the high score, but whatever. Right, and she has the second high score, which is 0.40, and that's great. So the model, if just ignore this part for a second, the model now knows that she is very important when it comes to kicked with respect to the sentence. But so far it only has a number, like it doesn't know what to do with it. By multiplying it with the v vector, it gives you the information about she itself. So this way the final output understands the context of kicked based on relevant words. And this is why multiplying with value vector is ultimately very important, because it, in my understanding, it basically independently tells you how important that word is. And the softmax basically tells you how important it is in relation to the word that you're trying to see. So if you look at this figure here, let's say that the Q1 is, let's assume each word is a token. So Q1 is she, Q2 is kicked, Q3 is the, and Q4 is ball. Same here, she kicked the ball. So with respect to kicked, Q2, we know that this value is going to be high because it's the dot product between this she and kicked. This value is going to be very high. And this is called an attention matrix, and this is how it's calculated for each word. And this is interesting because this is how the model has, it can have a lot more context, right? The bigger this matrix, the more context it can add, and of course the more parameters. And here is the main softmax function. That this is all the 8 steps that we're doing. So right, and this is the transformer architecture. We're going to talk about, don't look here, we're going to talk about this in a little bit, but yeah. Input embedding, positional encoding, multi-headed attention, and then feed forward. We know all of this now. Moving forward. Okay, so far we've talked about encoder, and decoder is basically the same except one tiny difference. The encoder has self-attention and feed-forward neural network. The decoder has self-attention and then cross-attention, and then the feed-forward neural network. Cross-attention basically takes the input values from the encoder. So let's understand why we need this. Self-attention, we already know it understands the relationship between different words of the same sequence, of the same input. But the cross attention, it calculates the relevance and dependencies between input and output. And it does so because in cross attention, the key value pair comes from the encoder inputs. And that's pretty cool. So, oh, you would think that, oh, now I get it, that's how LLMs work. You take the inputs from here and you calculate it with reference to the self-attention layer here, and that's how it's calculated. But you'd be surprised to know that generative AI models, which like the decoder-only models, they don't have cross-attention at all. They only have the self-attention layer. And yeah, cross-attention is used in only encoder-decoder models like T5 or BART, where decoder needs to attend to an encoder representation of the input. Decoder-only models like GPT, for instance, only use self-attention and do not have cross-attention at all. So it's interesting. And there's no need for cross-attention because there's no separate encoder processing the input. Instead, the entire model only consists of decoders that handles both input and output within the same architecture. We'll talk about it more in the coming videos, but just for the sake of completeness, basically they apply masked self-attention, meaning each token can attend to the previous token and not the future ones, because then it would be rigged and it would already see the outputs. But yeah, that's how GPTs work. Moving forward. Okay, talking about the last add and normalize layer. Now, you need to normalize the input after self-attention because otherwise you would have crazy gradients, like exploding or vanishing gradients, and it's used to make the optimization process more stable. Right, in the encoder, the add and normalize is applied after self-attention and feed-forward. In the decoder, it's applied after self-attention, cross-attention, and then feed-forward. So yes. Oh, and if the idea, so that's normalization, and then there's residual connections where you take input and then you take the direct input without processing and then connect it to the next layer. And if this rings a bell, you'd be right because we just talked about it in RNNs, and they're a very similar concept, but the only difference here is that the RNNs process this sequentially, but the transformers process this parallelly. So that's pretty cool. Okay, now we know add and normalize, why it's needed. We know residual connections. And this brings us to the end of the understanding of the transformers thing. This is the entire architecture. We understand softmax. We know what's happening in each layer. And yeah, this is the transformer architecture for you. We're going to discuss more about generative AI models like DeepSeek and ChatGPT and how they're different and what's new that DeepSeek has done. And we'll try to code a transformer in the coming videos as well. So, thank you.